Good morning. So today's topic is crystallography. So what is solid state physics? The study of solid state physics interpret the macroscopic properties in terms of microscopic properties of particles of which solid is composed. Means we are talking the macroscopic properties of particles in terms of microscopic particles. And crystallography means the study of geometric form and other physical properties of crystalline solids by using some X-ray electrobeams techniques in such a way, by using some X-rays electron beam techniques. We will study the geometric form and some other physical properties of crystalline solids. So, matter, it is divided into two things. One is the solids. We call it as crystalline solids and amorphous solids. Okay. Actually, elements and their compounds are found in three states that we call it as solid, liquid, gases. We are familiar with this. The matter is composed into three categories: solid, liquid and gases. But some solids are brittle. Some solids are brittle. Brittle means it is hard but easy to break. Such kind of solids. Some solids are ductile. Ductile means we can make them into thin sheets. Some solids are malleable. Means they can be pressed into or hammered into any shape. Okay. Some are good conductors of heat and electricity. Some are bad conductors of heat and electricity. Some are magnetic in nature. Some are non-magnetic in nature. So on. In such a way, solids are of different kinds. Alright? If atoms or molecules are arranged in a systematic manner in such a way, intermolecular distance will be fixed and arranged in systematic manner, then such solids we call it as crystalline solids. If atoms or molecules are not arranged in such a systematic manner, we call it as amorphous. We call it as amorphous. Okay, or irregular arrangement of atoms or molecules in a substance. We call it as amorphous solids. Right? Now, we are dealing in crystallography, we are dealing with crystal structure. Okay? We are trying to know about the physical properties. Okay? So, the geometric form in this chapter. So now first let us define what is crystal. So already we said that in crystalline solid each atom or molecule is fixed at a definite point in space at definite distance. They in such a way at a definite point they are arranged at a definite system. Okay. So this we are calling crystalline solid. So how to define crystal? Crystal is a solid composed of periodic array of atoms. We can say no. It is nothing but a solid composed of periodic array of atoms. That is, we can also say that a representative unit repeated at a regular intervals along any and all direction. Just if we take one particular point, this point you see it is repeating in all directions. or any one direction. So a representative, one particular unit, okay, one particular unit repeated at regular intervals along any or all direction. एक ले लेके the same thing it is repeating in all directions or any one direction. Now lattice. Lattice means periodic arrangement of atoms. So this we call it as lattice, periodic arrangement of atoms. Space lattice means array of points in space such that environment at about each point is same. So if you see the environment around each and every point, it will be identical. It will be same. So such we call it as space lattice. Lattice means periodical arrangement of atoms. Space lattice means the array of points, the array of points itself only, but the environment about each and every point will be same in that particular space. That we call it as space lattice, right? Now next, basis. Now this is lattice. The red color dots, lattice, the arrangement of atoms or molecules. Now see, in some solids, to this lattice, some atoms or ions, a single atom or ion or group of atoms or ions are attached. This we call it as basis. Here to the lattice point, some group of atoms or ions are attached. This we call it as basis. So this lattice plus basis give rise to the crystal structure. Okay, a set of more or one atom about lattice point we call basis. So crystal lattice together with basis gives crystal structure. Lattice plus basis is equal to crystal structure. Now next, let us move for the translation of a vector or basis vector. So these are the lattice points. So these lattice points, how to locate? With the help of the coordinate system only we will locate these lattice points in the space. Okay. For example, consider a coordinate system with origin A. Let it be origin A. I considered a coordinate system with origin A. So here A, B, C are nearest non-collinear points. Okay. So A, B, C. How these are? A to C, B. Nearest non-collinear points. Let us assume AB equal to A, AC is equal to B. Here A and B, the small letters A and B, we call it as coordinate vectors. Then how to write the position vector? So the position vector of lattice is expressed as R equal to N1A plus N2B, where N1 N2 are integers, means which number of lattice point is that? That integer whose values depends upon the location of lattice point with respect to origin. The location of first lattice point or second, the location of lattice point with respect to the origin. Okay. Now, if we take three-dimensional also, we can write N1A plus N2B plus N3C. Where A, B, C we call it as primitives. We call A, B, C as primitives. Now next, let us move for unit cell. So unit cell means, now if we construct a home, what you will do? You will use bricks. In a translatory mode, you will arrange the same bricks one over other. Right? So one over other, you will repeat on arranging the same bricks which are identical to each other. So that give rise to a wall. In such a way, a smallest geometric figure, the repetition of a smallest geometric figure gives crystal structure. Okay. So now here you see, here these are lattice points. We are considering two-dimensional crystal in which the atoms are arranged, which we call it as lattice. If we consider a parallelogram ABCD with a side AB equal to A, AD equal to B, then by rotating this parallelogram, so the whole crystal lattice may be obtained. Now this one, next this, next this, next this. In such a way, by rotating this parallelogram, the whole crystal can be formed. So this fundamental unit ABCD, we call it as unit cell. So if this cell repeats regularly, give rise to the actual crystal structure. So in such a way also we can take, or in such a way A double dash, B double dash, C double dash, D double dash. Okay, it should be noted that choice of unit cell is not unique. Compulsory, we can't say that unit cell must be in such A, B, C, D parallelogram only. The choice of unit cell may be A dash, B dash, C dash, D dash, A double dash, B double dash, C double dash, D double dash. Okay. So, it totally, the choice of unit cell conveys the symmetry of crystal structure and mathematical calculations easily. So, the choice of unit cell is not unique. It can be constructed in any way, in such a way or in such a way, in any way. So, one small part we will take, unit we will take, and we go on repeating. If we go on repeating that unit, we get unit cell. So, what we can define unit cell? So, unit cell, it is defined as, either you can say that fundamental elementary pattern of minimum number of atoms, molecules or group of atoms which represent full characteristics of crystal. The fundamental pattern of elementary pattern of number of atoms, molecules or group of molecules represent fully the characteristics of crystal, or simply we can define the volume of solid from which entire crystal is constructed by translation repetition. Now see, this is translation repetition. No? I am taking the example of ABCD. Okay. The entire crystal is constructed by translatory repetition in such a way. In 3 dimension, I gave the example of wall construction. No? The identical bricks, we will take the identical bricks, we will arrange in translatory mode, one over other, side by side, in such a way. And at last we will get a wall. In such a way, a volume of solid from which entire crystal is constructed by translatory repetition in 3-dimensional. We call it as unit cell. Okay. Now next, lattice means the periodic arrangement of atoms. I said no. There are 3 types of lattices. Simple or primitive cubic, or simply we call cubic P type lattice. Face centered cubic lattice or cubic F lattice. Body centered cubic, that is b.sc we call, or cubic I lattice. Now let us go for this types of lattice and then let us move for 7 crystal system. Right? So first, simple cube. Simple cube means these are the 8 corners of the cube. At 8 corners we have a lattice point. One unit cell we took and explaining about that. One lattice point will be at 8 corners. Okay? And inside this unit cell there is no lattice. You see, at corners only I just draw these lattice points. Inside the unit cell we are not having any lattice. each lattice point each lattice point is surrounded by 8 unit cells. Each lattice point is surrounded by 8 unit cells. Means one lattice point is member of 1 by 8 cell, we can say, no. Okay, एक lattice point के अतराप 8 unit cells है. So what we can say? 8, it is surrounded by 8 unit cells. So share of that each lattice कितना रहता? 1 by 8 plus 1 by 8 plus, like that 8 unit cells will share 1 by 8th part of this lattice point. They share 1 by 8th part of this lattice point. 8 cells are surrounded by one single lattice, so share is 1 by 8. So number of lattice points in unit cell, 1 by 8 into 8. 1 by 8 into 8, that is 1. So number of lattice points in unit cell is 1. Now next let us go for the face centered cubic lattice. As usual, at corners we are having 8 lattice points. Each lattice point is a member of 8 unit cells surrounded by it. So the share of each the share of each lattice point to cubic lattice, 8 into 1 by 8, 1. And we are having 6 faces, no? In each face again one lattice point will be there. We are having 6 faces. In each face one lattice will be there. And again these face centered lattice points are surrounded by, these face centered lattice are surrounded by again 2 unit cells. Okay, they are surrounded by 2 unit cells. So now here what happens? Again each being the member of 2 cells, no? The share will be 1 by 2, no? 1 by 2 plus 1 by 2, 1. Again each lattice point at the face center is surrounded by 2 unit cells. So share will be 1 by 2. So in such a way 6 faces are there, no? So now the total number of face centered lattice points with unit cell is 6 into 1 by 2. 6 faces are there and each is surrounded by 2, each being the member of 2 unit cells. So the share will be 1 by 2 into 6 faces, that is equal to 3. So number of lattice points becomes 3 plus 1. Here at corner 8 unit cells are surrounded. So share is 1 by 8. Here 2 unit cells are surrounded. Share is 1 by 2. So here number of lattice point becomes 1 by 8 into 8, 1. 6 into 1 by 2, 3. So total lattice points 3 plus 1, 4. Similarly body center. At center, as usual, at 8 corners 8 lattice points will be there. Each lattice point is the member of 8 unit cells surrounding it. So the share is 1 by 8 into 8 unit cells, 1 lattice point. And at center of the crystal lattice, at the center of the unit cell, we will have 1 lattice point. So that 1 plus this one, 2. So 2 lattice points are present in body centered cubic lattice. Now let us calculate the most important formula for doing the problems. Note down this formula. Okay, calculation of lattice constant. So A, lattice constant, rho, density of crystal, volume will be A cube, mass will be density into volume. So rho A cube. If n is the Avogadro number, what is Avogadro number? Number of n molecules per kg mole in substance. How many molecules are present in a kg mole of substance? That we call Avogadro number. So mass can be written as molecular weight by Avogadro number. Mass of each unit cell becomes n into m by n. So rho A cube equal to n m by n. So from that we get A equal to n m by rho n. whole to the power of 1 by 3. Right? So now this is the formula for lattice constant. Rho density and Avogadro number, molecular weight, and here n becomes number of unit cells. Right? Now let us go for the 7 crystal structure. Right? So here we are having 7 crystals. First one, cubic. The primitive signed interface angles will be A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees, and examples are NaCl, CaF2, etc. And this is the structure of cubic crystal. So 88 corners, 8 lattice points are there. Alright. Now next, tetragonal. A equal to B not equal to C, alpha equal to beta equal to gamma equal to 90 degrees. This is the structure A equal to B but not equal to C. So NiSO4, white tin are some of the examples. Next, orthorhombic. Here lengths are not equal to each other but angles are equal to 90 degrees. So A not equal to B not equal to C. Examples are potassium nitrate, KNO3, BaSO4, barium sulfate, etc. Next, monoclinic. This is the structure A not equal to B not equal to C. Angles alpha, gamma are 90 but beta not equal to 90 degrees. Examples are FeSO4, Na2SO4, etc. Next, triclinic. A not equal to B not equal to C. Alpha, these angles are also not equal to 90 degrees. And this is the crystal structure, and some of the examples are CuSO4, etc. Now next, rhombohedral, or we can also call it as trigonal. Here length again becomes the same but angles not equal to 9. Each angle is equal to each other but that angle is other than 90 degrees. Example, calcium sulfate, etc. Now the 7th one is hexagonal. A equal to B not equal to C. And this is the crystal structure. And alpha beta angles are equal to 90 degrees and gamma 120 degrees. SiO2, etc. are some of the examples. Okay. Now next one, bravais lattices. Bravais in 1848 he said that there are 14 independent ways of arranging points in space so that environment looks same from each point. Let us see that 14 independent ways of arranging 14 independent ways of arranging the points in space. The lattices are called as bravais lattices. Now as usual we know that 7 crystal system are there. That 7 crystal system can be arranged in 14 ways. How? Cubic crystal can be arranged in 3 ways. Simple cube, face centered, body centered. Tetragonal crystal can be arranged in 2 ways. Simple cubic, body centered cubic. Orthorhombic crystals can be arranged in 4 ways. Simple cubic, body centered, face center, base center. Base center means at base we will find 2 points, lattice points. Now next, monoclinic can be arranged in 2 ways. Simple cube, base, body centered. And rhombohedral, hexagonal, triclinic can be arranged only in 1 way, that is simple cube. Now see, 3 plus 2, 5. 5 plus 4, 9. 9 plus 2, 11. 12, 13, 14. In such a way, these 7 crystal system can be arranged in 14 independent ways so that the environment looks same from each point. So this is about 7 crystal system and bravais lattices. Thank you.